Okay, so when we stopped on our last video, we were talking about modeling that treatment condition that's typically dichotomous but doesn't have to be, as we mentioned. We're just going to assume easiest case here and leave it dichotomous for now. So this is going to be a function or predicted by the covariates that you include on those conditioning covariates, those confounding variables. So your outcome is going to be that propensity score estimation. If it's dichotomous, this makes you think, right, of a logistic regression model, because we would be predicting a dichotomous variable using a set of covariates. And in fact, it is a lot of the time. Now, there's some slight variations you can use, like, for example, if you have more than one outcome, you might use a multinomial model. If you have ordered outcomes, you might use a proportional odds model, or another ordinal model. There's a lot of other techniques you can apply, such as a boosting algorithm to improve the precision of this predictive model. But in general, it's best just to think of this as a logistic regression model. You want to make sure that you do not include that disease outcome that should not be included as a confounder, because it ultimately is that thing that you're going to try to be modeling in your full model once you have the propensity scores estimated. Remember, estimating the propensity scores is not the goal here. It's just a method we use for our end goal, which is more reasonably modeling that disease outcome using semi-equal groups, kind of a simulated treatment control group. So that propensity score is just a logistic regression model. You can use your propensity score using a continuous variable or create quantiles. I like to do both. If you work with me ever on a project, I will attempt to model everything 5 or 6 different ways, and I don't drop that philosophy when it comes to propensity score. I like to keep it as a continuous. I also like to create quantiles and think, if I see the same effect by both that continuous version of those scores, and those scores, by the way, are going to be between 0 and 1 because they're probabilities when you use a logistic regression type model. So they're just scores between 0 and 1, but on a continuous scale. And then I also split them into quantiles. You just use like a ranking function. It's pretty programmatically easy to do. So why not do that? And I like to use that for like a stratified model, and then maybe compare that with propensity score on a continuous scale for a matching model, in every combination I can think of. If everything looks the same and I get generally the same results, not obviously the same numerical results, but the same research conclusions, then I pick what, seems the clearest, the most transparent, the easiest to interpret, or something like that, because I would get to the same research result using any model. And that to me just gives me more assurance that I have something reasonable in the end. Okay, next slide if I can get there. There we go. So this may seem a little confusing, because remember, E plus is our treatment condition. So E plus is the treatment, E minus is the control. Why would we be estimating the probability of E plus when we already know it? Well, because this is giving you the probability of that treatment condition, given all these things that we believe are related to that treatment condition. So think back to that medical example we were talking about in the last video. Say you're looking at aspirin use among people and incidence of a heart attack, okay? And being a male of a certain ethnicity and of a certain age group will either will disincline you to taking your aspirin every day. Let's just say that, okay? So we would say that those variables should be included as covariates, because they're going to be good predictors of that E plus condition, that condition of whether or not the person, not the man, the person takes an aspirin daily, okay? Once we're able to predict that, then we have this information, this observed probability that helps us create equivalent groups. Okay, so imagine for the people who take the aspirin every day, do the aspirin therapy every day, and those who do not, so the E plus and the E minus patients, some are going to have really close propensity scores. And you can imagine that they get just randomly assigned to each of the group because they have the same characteristics. Okay, that is, subjects in those two groups, the treatment and the control groups with nearly equal scores, propensity scores, tend to have similar distributions of those covariates. Those covariates are really similar. And for some reason, one of them took the aspirin every day and another did not. Okay, and so we can use that now, that near equivalency or similarity, to help us now create very similar covariate groups. So we use this thing called a balance table typically, and what this does is it says for a particular propensity score, one gets some average effect for that treatment. Okay, this is of course estimated using some often large number of covariates. For example, this is all from the presenter on propensity scores I saw years ago. Lisa, she said this original paper applied the propensity score methodology to an observational study. They had 74 covariates. Now, I've never had that many. Okay, that I'd have to probably run on a batch submit to my server or something. Okay, but you can do that. Then you want to make sure that your propensity score is adequate for adjusting those effects of those covariates by testing for differences of those covariates used to predict the treatment control conditions after adjusting for the propensity score. So this is what we call like a balance table in practice, is that table that shows us how close are these groups after we've adjusted for a propensity score. Okay, so after you've done all this work of estimating the propensity score, you get to the application stage. You can do this by the two primary methods used, and most of the time are either matching or a regression adjustment / stratification. I usually call it PS stratification. Weighting is kind of used some. I believe that current practice kind of discourages using weighting, so I don't ever use it. I believe that's the last I read about it, and it seems like stratification and matching are always more suitable to me. But maybe somebody out there knows why you'd want to use weighting instead. So let's say, let's get back to like a more concrete situation here. You match on a single summary measure. So again, the aspirin mortality example. Age is a strong confounder, but it can be controlled by matching. So the idea here is that maybe older people are more likely to take their low dose aspirin. And so then you might go, well, hey, young people and old people are just as likely to die of a heart attack. But really, use of the aspirin is confounded by age. So you're really not able to say that. Or you would have said it the other way, actually. Low dose aspirin does not make a difference. But really, it's confounded by age. So extending this to a lot of factors can get really numerically complex, and that's why I talk a lot, or I think a lot, about the stability in the model, as I mentioned earlier, because you're using that logistic regression model, and it's pardon me, it's really easy or commonplace in logistic regression models to experience quasi-separation, which really makes your model unstable. So I like to use like a boosting procedure to stabilize those estimators across multiple resamples. Okay. So enough on that. That's a practice issue that I'm not going to really get into much. But this is a technique that's really super useful when you have a limited number of the treatment patients and a lot of the control. This happens a lot when you have like a new experimental treatment or something. Maybe you only have 30 research subjects that are using this new medical device or something, but you want to be able to make a good comparison to those without it, but you don't have, they weren't randomized. This would be a very good one because you can actually do like one-to-N matching here, which I would really recommend. Okay, so matching techniques include things like nearest available matching based upon an estimated propensity score. That is probably the most common, I would think. You select a positive or treatment subject, then you find somebody in the control group that has the closest proximity score. You have to set like a window for how close is close. So, because remember that those propensity scores are on a 0 to 1 scale. So how close is close? Is 0.01 close enough, or is 0.02, or is 0.05? So you want to match those windows. A lot of software allows you to match also based upon individual variables as well, which is really nice. You repeat until all your E+ subjects are matched. This is easiest with regard to computational issues. Other things can be used. So for example, Mahalanobis distance metrics can be used. I've seen nearest neighbor algorithms used. But anything that kind of is like a algorithm used for finding similarity among observations. So not similarity, don't get confused with like those hierarchical clustering algorithms, but similarity among the observations. Those you want to use to try to find, quote, similar propensity score, or similar measures. You may or may not be using always the propensity score, by the way. Generally you do. So if you use something like the Mahalanobis metric, you just get the minimum, and those are your two matches. The problem is, I think determining a rule of thumb is a little less intuitive than using like a standard matching algorithm. I have a harder time. Okay, so most often if I'm working in R, I use the Twain package. I'm going to attach some code for showing you how this gets performed. The PS generally performs the propensity score matching, but if you have more than two outcomes for your treatment variable, then you want to use M and PS. It's actually lowercase m, sorry, not uppercase. So that does multivariate. IT got switched there, and PS matching. I should have read better. The balance table provides a variety of univariate tests to determine if a balance exists. Okay, so this is just a very brief overview of code that's pretty easy to use, I think, in R. In SAS, so they do have a new proc PS match, but it's not, most people don't have a release of SAS that includes this. So what I've used instead is the Gmatch or Vmatch. Gmatch uses a greedy algorithm for matching with a fixed number of controls per case. You could choose, so you get a little bit more flexibility with the SAS algorithms, to tell you the truth. These are macros in SAS. Because you can choose, like, I'm going to do 1 to 5 matching because I have a lot more controls than I have cases. Things like that. Variable optimal matching is performed by Vmatch. The total number of controls per case is allowed to vary with only the total fixed here. So it's a little bit different. Controls can be matched to cases using any number of factors with both of these, both Gmatch and Vmatch. But let's look at some applications and just think through why propensity score matching is useful here. So these are actual published articles. Here we have the effectiveness of right heart catheterization in the initial care of critically ill patients. We're going to pick up on this in the next video.